So now I want to teach you specifically about projectiles above the ground. And what that means is normally when you have projectile motion, we have questions that start at the origin there, 0, 0. So it starts from there. But now we're going to explore what happens if you throw an object off a cliff or a platform above the origin like that. And it poses some unique questions, which we're going to go through later. Question 2 here, we're going to use the origin as a base of the cliff, and we're not going to care about air resistance, and we'll take gravity as 10 meters per second squared. And the cliff is 35 meters above the ground. The angle of projection is 45 degrees and velocity is 16. Now, the point of this module here is to teach you specifically about when we have projectile motion above the ground. So when we do questions like 2A, where we want to derive the equation of the horizontal displacement, we're not going to go through all the steps just because it takes too long, but you know for yourself that in an exam, that's what you need to do. Firstly, the horizontal displacement equation, we can just use that there. And just substituting this equation, where V equals to 16 and 45 degrees is our angle, gives us 8 square root 2, and that's because we have 16 times 1 on square root 2, which is square root 2, and then you just quickly rationalize that. So you get 16 square root 2 on 2, which cancels down to 8 square root 2, like that. So that is our horizontal displacement equation. Just going to emphasize again, we're just doing this because for the sake of time, we want to focus on some questions later on, but in an exam, you have to start off with acceleration and then integrate until you get that horizontal displacement equation. All right, what about the vertical displacement equation? Just using this down here, we're going to substitute in the various values. We said gravity would be 10, so we substitute that in. Our velocity is 16, 45 degrees. And now this 35 comes from that 35 there because it's 35 meters above the ground. So that's why we add 35 with our horizontal displacement. So now some simplification. Negative 10 divided by 2 gives us negative 5. Here we have 16 times 1 on square root 2, which was 8 square root 2t plus 35. So this is our equation for the vertical displacement. And just remember with that, if it's going up by 35, you add 35. If it was above the ground by 100, you add 100. So pretty simple to know what you need to add for that. Now we've worked out the horizontal displacement equation and the vertical displacement equation. We're going to use both of those to work out the equation of the trajectory. So remember, the trajectory occurred when there was only x and y. So we need to eliminate t. And to do that, we're going to start off by using this equation here. And all we've done is divided 8 square root 2 onto the other side. So we get t equals to x on 8 square root 2. And now we're going to use this equation. And all we're going to do is wherever there's t, I'm going to substitute in x on 8 square root 2. So here we have that equation. And wherever there's t, I've substituted in x on 8 square root 2. And t here, exactly the same thing. Just cancel that. There's really nothing else much you can cancel. So just a bit of working out. So that becomes negative 5x squared on 128 plus x, just by itself, plus 35. So this here is our equation of the trajectory, which all we need to do is eliminate t by rearranging our horizontal displacement equation and substituting that into our vertical displacement equation there. Let's move on to this one, which is where we want to calculate the time the stone will take to land in the water. Think about that. That means the time the stone will take to land in the water still occurs when y equals to 0. So it still occurs when the displacement equals to 0, okay? So that's not affected by the fact that it's thrown off a cliff. That means we want to take this equation over here and make it equal to 0. But the only difference here is because we have that 35 there and it's not just 0, it means we can't factorize out the t like we normally would to work it out. So in this case, I want you to use a quadratic formula. All right, and remember, what was that? So that's going to be negative b plus or minus square root b squared minus 4ac on 2a. All right, and that's one big thing here that you see when we put that in. So negative b plus or minus b squared, so that was 128, minus 4 times a times c on 2 times a. And just put that into your calculator. Be a little bit careful. What I would do is work that out first, square root it, and then put it together, because otherwise just too many things going on. And then using that equation, we see that t can either equal to 1.75 or 4.01. Now, because of the nature of our diagram, you can see that negative 1.75 would be over here, which doesn't exist in projectile motion, and that makes sense because negative time doesn't exist in real life either. So that's why we take our 4.01 as the time of flight. So it actually takes 4.01 seconds for this stone to land in the water, right? So time of flight, even when we do have above the ground, it doesn't really change anything. It's still when y equals to 0, when it hits the ground. Okay, well, what about when we want to calculate the distance from the foot of the cliff? How are we going to do that? When we normally just have a projectile, so if we were starting from here, we talk about the range of the horizontal motion, and that's very similar to when we want to calculate the distance from the foot of the cliff. Because looking at that diagram there, the distance from the foot of the cliff is given to us by that there, right? And all that is your horizontal displacement at the time that that hits the water, which is your time of flight. Which means all you need to do is use your horizontal displacement equation there, which is 8 square root 2t, substitute in the time of flight, like that, work it out, and it just equals to 54.37 meters. What you've worked out is that distance says 54.37 meters, and it's similar to your range of your motion here. So that's what I want you to think about when you see calculate the distance from the base of the cliff or base of the platform. Calculating its maximum height. Do you think there's going to be a difference here because it's going off a cliff or not? Well, not really, because what you see is the maximum height still occurs when your displacement equals to 0. Your velocity equals to 0. So it still occurs here when your vertical velocity equals to 0, when it stops at the top. That's not going to be affected at all. So we're still working out that there, the maximum height of that, which means that we need to firstly find out our vertical velocity equation. All you can do is have a look here, and that is our vertical displacement equation, and just differentiate that. So differentiating this, take the 2 down, that becomes negative 10t, this becomes 8 square root 2. So this is our vertical velocity, and make that equal to 0. And for this one, 8 square root 2 equals to, just move over the 10t, divide both sides by 10, and that's how you get, so remember here we have 8 square root 2 on 10, and that's how you get 4, just cancel down, 4 square root 2 on 5 as t. So remember, that was the time that you get the maximum. Yeah, so that's not your final answer, that's just the time that you get the maximum. To work out the actual maximum, we need to use our vertical displacement equation here and substitute in the time of 4 square root 2 on 5. So substituting in t squared for that, and t becomes that as well. And now with this, I think the best way is just put into your calculator. Don't need to do any more work than that. And we get 41.4 meters. So that there is 41.4. Just be wary here that when we talk about the maximum height, it's maximum height of the projection. So naturally it would go down to the ground level, okay? It has nothing to do with the starting level at all. It's still going down to that 0 level there. Good. So that's calculating the maximum height.